Hi there, this is Dr. Hisham Said. In this video, we'll go over an example of how to calculate the resultant of forces and identify its magnitude and direction. So here we have a ring bolt. So it's kind of bolted into a structure. You can say it's tied into three cables. Every cable is pulling the ring, so you have a tension force. All of them are tension forces with different values and different directions. And the design requires that you identify the resultant force in Cartesian units, and you summarize that in a different way, which is by calculating its magnitude and direction. So for part A here, Cartesian units means that we need to identify or represent R in terms of its x and y components in the I and j directions. So R as a vector force is equal to Rx in the I direction or the x direction plus Ry Ji in the y direction. And how to find the x and y components of R is to add the x and y components of the forces that we have. So Rx will be the sum of x components of the forces, and when you do that, you have to get the x components through the angles that are given to us. So for example, the 5 kips, the right force here, it has a 40-degree angle with the x-axis, so it's cosine 40. The 7 kips has a 70-degree angle, 50 plus 20, and it's component the x is cosine 70, but we have to pay attention to the direction here. So the x component of 5 kips is going to the right, but the x component of the 7 kips and the 9 kips are going to the left, so it's negative. So pay attention to what angle you're dealing with for each force. Are you dealing with cosine or sine? In our cases here, all the angles are measured from the x-axis, so it's all cosine components. And you have to pay attention to the direction. Look at the figure and visualize the direction of each one of these forces to decide if you're plugging it into the formula as positive or negative. So we end up with the net here to be negative 7.02 kips. We'll do the same with Ry, but we're focusing on the y components. And you can see here we're following almost the same structure of the formula. So because we have the same forces that we're calculating the components for. So it's the 5 kips, 7 kips, 9 kips, same angles, but now we're flipping now the trigonometry. So instead of cosine, we're dealing with sine. And you end up here with all the forces. You can see even all of them are pointing to upward. So the resultant will be the addition and the accumulation of the y components to be positive here. So in summary here, R as a vector will be equal to that Cartesian vector. And just to always remember to write the units. So I do this mistake always, but try to always remember to write kips as the unit. Kips here stands for kilo-pounds, kilo-pound force. So we're done with part A. Part B is looking at a different representation of the force vector by calculating the magnitude and the direction. And the magnitude here is the square root of the component of the vector to the power 2, the addition of these values. So doing just that simple math here, you will end up with the magnitude of the force here. It's a scalar value. It's not positive or negative. It's a scalar value of 14.66 kips. The direction, now, that's I recommend, so the direction, it's a formula, you can apply it right away, but I recommend that you visualize the directions of the x and y components, and if you're dealing with 3D, then the x, y, z components. But if I see here that the x component is negative, so I go to the left, and this is Rx, and then y component is positive, so I go to upward, So the resultant here is equal to 14.66 as the resultant of these two vectors. But I can see here that the resultant is going into the second quadrant to the left. So when I start now using the theta equation here, which is the tan inverse of y components over the x component, I expect to see an angle measured from the positive x direction to be bigger than 90 degrees. So when I plug in the values for ry and rx, I plug it in with their signs. So y is positive, x is negative. So I end up with tan inverse of a negative value. So it will give you, if you do it on the calculator, it's giving you negative value of 61.39. Now, how this 61.39 relates to the visualized angle on the figure, it's actually the one that adds up to 180 degrees to theta that we want. So the actual theta that we want measured usually measure the theta, the angles from the positive x direction. So here in this case, theta is equal to 180 minus 61.39, so you end up with 118.61 degrees. So I recommend again try to be visual, try to follow the direction of the components you're calculating the resultant for them, and that will help you to make any adjustment for negative values that you have in the tan inverse formula. So that concludes our example. I will see you in future videos. Thanks for watching.